Hello everyone, welcome to this video. In this video, we shall be looking at another property of compact linear operator. So basically, we are going to talk about the range of compact linear operator. So here in this video, we are saying that this range of compact linear operator that is closed, right? So first of all, let me remind you what we were doing. So we were considering a linear operator T, right, from some space X to the normed space X to the same normed space X, and we are defining this T to be the compact linear operator. This is given to us. We are assuming this thing. So corresponding to this T operator here, we are defining another operator T lambda, which is nothing but T minus lambda into I, where I is the identity operator. So now once we have T lambda, so when we compose T lambda onto T lambda, so what do we have? T lambda square, right? So this is another operator, and similarly when we compose T lambda square onto T, so T lambda, so we would have T lambda cube, and if we keep on doing like this, we have some sequence of operators saying T lambda square, T lambda cube, and so on. So what is the effect of all these operators on the range for a given compact linear operator T and for a particular value of lambda which is not equal to 0. So let's have a look onto this. So the result that we are going to study today is about the range of compact linear operator. It is closed. For a bounded linear operator, we know that the null space, that is always a closed space, but the range, that need not be a closed space, right? This we already know about bounded linear operators. But what can we say about compact linear operator? So when T is compact, when the given operator T, that is a compact operator, in that case T lambda would have a range that is closed for every lambda. So that means for every complex number which is non-zero, this T lambda has a range which is closed, and the range for the operator T lambda square, T lambda cube, and so on, that is also closed, right? So the theorem that we are going to study today, that tells us about this closeness of the range. So the statement here is that for a given operator T, which is defined onto the normed space X, to the normed space X, this is given to be a compact linear operator. Then for every complex number which is non-zero, the range of the operator T lambda is closed. So this is the result here. For proving this result, we have to divide our proof into three parts. So as usual, we'll proceed through the process of contradiction. So we'll proceed through the process of contradiction, right? So here we assume that the range for the operator T lambda x, that is not closed. If this is not closed, how can we proceed and reach at this contradiction? So in this case, we'll take three cases. So using these three results, we shall be proving our contradiction. So the first result that we are going to prove is that because we are saying, now in this case we are saying the range T lambda is not closed. So you can see this thing as like this. Suppose there is some y which is present in T lambda x. So which is present in the closure of T lambda x, but it is not there in T lambda x as such. So if this is the case, then we have a sequence T lambda of xn, right? So all of these xn's, they are the members of capital X, the norm space capital X, right? So this sequence T lambda, when applied onto xn, this converges to y. This is the first thing. So assuming this thing, we will show that this xn, this does not belong to the null space of T lambda, but this null space of T lambda, it contains a sequence Zn such that the distance of all of these xn with this Zn, this sequence Zn, is less than equal to 2 times delta n. where what is this delta n? That is the distance from xn to the space, to the null space t lambda. So that means, suppose if this is the null space of the operator t lambda, so in this case we are saying that whatever is the distance of xn from every element here, so that is less than 2 times of delta n, right? So basically this distance delta n, that is the distance from xn to n t lambda, right? So this is the first point. Next, using this point we shall be proving that if we consider the distance between xn and zn as an, so that means the norm of xn minus zn as an, so in this second case we shall be proving that this distance goes to infinity. That means these 2 points, they are very far away from each other. So this is one thing, and using this thing we'll again reach the final contradiction by proving that there is a sequence wn where wn is equal to the sequence xn minus zn divided by an. And what is an? The norm of xn minus zn. So basically your wn is nothing but the sequence xn minus zn divided by the norm of xn minus zn, right? So by considering this thing, we finally are going to reach our so-called contradiction, which would then prove that the range is a closed set. So we are starting our proof by assuming that the range is not closed, right? So let's see, what do we have? So we suppose that the range of the operator t lambda, so that means t lambda of x, that is not closed. If this is not closed, so what does this mean? It means that there would be some member y which is there in the closure of the range, so that means t lambda of x closure contains y, but this y is not there in t lambda x itself. And for this y, because we are taking this y from the closure of t lambda x, right? So that means it would have some form of this kind, t lambda x kind, right? Where x is some member of capital X. So we would say corresponding to this y, there is also a sequence xn in capital X, the normed space capital X, such that yn is nothing but t lambda of xn. So this thing converges to y, and this limit point, the y here, is present in the closure of the range but is not there itself in the range, right? This is one point. So we are marking this as equation number 1. So we are saying yn is converging to y, where what is yn? Yn is equal to t lambda of xn. So this is first point here. Now because t lambda x, that is itself a vector space. Why? Because that is a part of normed space, right? So obviously it would contain 0. If this contains 0, right, and we are saying y is not there in t lambda and 0 is there in t lambda x, right? So that means y cannot be 0 in itself. If y is not 0, that means what was y? If this is not 0, so obviously yn would also not be 0 because this is converging to y. So yn is also not 0. If yn is not 0, what was yn? It was t lambda of xn. So if yn is not 0, that means we are saying t lambda of xn is not equal to 0. If this is the case, so using the definition of null space, if this was 0, we would say xn belongs to the null space. But because this is not 0, this thing, by the definition of null space, we would say xn is not there in the null space of t lambda. So this is second point that we have. Okay, next we are saying that these 2 points, they hold for every n. Now because we know for a bounded linear operator, the null space of the operator that is closed. So if that is closed, that means the distance delta n, what was this distance? It was the distance of all of xn to the null space. This distance is positive, right? So we define this distance as the infimum of the distances of xn from all the z which are taken from the null space of the operator t lambda. So this distance is obviously greater than 0. Why? Because the limit point is outside of the null space. Okay, so that means using the definition of infimum, we would say, because this distance is greater than 0, we would say there is some sequence Zn in n t lambda such that the distance of xn with Zn is less than 2 times of delta n. Right? The distance of xn with Zn. What was Zn? Because we are talking about this infimum here and we are taking the distance of xn with z. So we would say there is some sequence Zn in the null space of the operator t lambda such that the distance between xn and Zn, which we are calling by an, is strictly less than 2 times of delta n. Right? So this is one thing. You can see this thing by seeing that when you add and subtract Zn from it, obviously where is it? It is there in the null space of operator t lambda. And where is the sequence Zn? So it is also there in the null space of the operator t lambda. So obviously the distance between z and Zn is going to be less than delta n, right? Because that is the infimum and we are taking the distance of xn from z. So overall, when you add and subtract Zn from here, you will get an as strictly less than 2 times of delta n. So here we have proved our part A. So let's again have a look here. In part A, we considered some number y here, which is there in the closure of t lambda x, but that is not present in t lambda x itself. And the sequence t lambda xn converges to y. In this case, xn does not belong to the null space of t lambda, but this null space would contain another sequence Zn such that the distance of xn with Zn is strictly less than 2 delta n, where what is delta n? That is the distance from xn to the null space itself. So in the second part, we are required to prove that the distance between this xn and Zn, that is infinite, right? So we are calling this distance as an. So this distance is infinite. This we have to prove in part 2, part B. So let's proceed. We have to show that an, which is the norm of xn and Zn, that is infinite whenever n goes to infinity. So we again move with the method of contradiction. So here we assume that this thing is not true. So that means this distance, this an does not converges to infinity, right? So that means if this does not go to infinity, that means the sequence xn minus Zn, it has a bounded subsequence. So that means it has a bounded subsequence. So what is that subsequence? It has a bounded subsequence. Why? Because now the distance is not proceeding towards infinity. So, okay, so this is one thing. Xn minus Zn has a bounded subsequence. Now the operator t is given to be compact. This we already know. So this sequence, this is present in obviously in the normed space X. So when we apply the operator t onto this sequence here, it would have a convergent subsequence. Why? Because the operator t is compact and we can use the compactness criteria here. We can use compactness criteria here. So according to the compactness criteria, the sequence t of xn minus Zn has a convergent subsequence. Okay, so this is one thing. Another thing, we know what is T lambda. T lambda is T minus lambda I, and lambda, that is some complex number which is not equal to 0. So using this expression, we can extract I from here, identity operator. So we can shift this thing to this side, this thing to this side, and then divide by lambda, or pre-multiply both sides with lambda inverse. So we have I as lambda inverse of T minus T lambda, right? So again, because all of our Zn, this sequence was there in the null space of T lambda. Therefore, whenever we apply T lambda onto Zn, it would result in a 0. So using this thing here, and because Zn was there in the null space, what do we want? We want the difference of xn minus Zn. So this difference, so what is this? Xn minus Zn. So we can write this thing to be I times of identity operator, this times of xn minus Zn. And what is the operator I? That is defined here, right? So it is 1 by lambda T minus T lambda of xn minus Zn, this thing, right? So once you have T applied onto xn minus Zn here, and then you have T lambda applied onto xn minus Zn. So basically you have 1 by lambda T xn minus Zn, right? And then minus of T lambda applied onto xn minus Zn. So now when you open up this thing, T lambda of Zn, this thing is equal to 0. Why? Because Zn was there in the null space of T lambda. So we are left with this thing over here. So from here, see, what do we have? From here we have that xn minus Zn, that is this thing, right? Okay. Now from the result here, we have a result here that T of xn minus Zn, this has a convergent subsequence. So using this result, it would have a convergent subsequence, and T lambda of xn converges using equation 1. So let's go back to our equation 1. So here equation 1, T lambda of xn, which was nothing but yn. So we have proved here that yn converges to y. So obviously T lambda xn would also converge to y. So let's go back. So T of xn minus Zn, we are saying this has a convergent subsequence, one thing. Another thing, T lambda of xn, this converges using the above result. So therefore, we would say that because both of them, they have convergent subsequence. Therefore, the sequence xn minus Zn, it has a convergent subsequence. And what is that convergent subsequence? So let's call that subsequence as the difference of x of nk minus z of nk, where k denotes the index for the subsequence. So their difference, this is the sequence, and this sequence converges to some member here, which we are calling by v, right? So this is another result. Next, now because T is a compact operator, this is the one thing that is given to us in the theorem, and T is continuous. Now because T is continuous, so what is T lambda? T lambda is T minus lambda I. It is a linear expression in T, right? So because T is continuous, so T minus lambda I is also continuous. And if this is continuous, now you must remember this result, the continuity result. If you have a mapping, then if xn converges to x0, then T applied onto that would also converge, right? If the mapping is continuous. So here, because T lambda mapping is continuous, and we are saying x of nk minus z of nk, that converges to v, in that case when you apply T lambda onto that also converges, right? So T lambda of x nk minus z nk, that converges to T lambda of v. Now, because you know Zn is there in the null space of T lambda, then T lambda of Zn k is equal to 0. Right? And we can again use equation 1 that tell you about equation 1 tells us that T lambda of xn, that is yn, that converges to y. So this was according to equation 1. So using equation 1 we have this expression. If we consider this expression T lambda of xnk minus znk, so it would be T lambda of xnk minus T lambda of znk, right? So here this thing is 0 because Zn is present in the null space of T lambda, so its subsequence is also present in the null space, right? So we are left with T lambda of xnk. So this thing converges to y. Why? Because xn has the subsequence xnk, so this would converge to y. Hence we can say T lambda of v. Why v? Because we started with this thing and this thing converges to v, right? Above here. So T lambda of xnk minus znk converges to T lambda v, and next thing we are saying T lambda of xnk minus znk, that converges to y. So that means this thing here and this thing here, both of them, they are equal. So what was that? T lambda of v is equal to y, right? So from here you see that what is y? Y is T lambda into v, where what was this v? V was some member in x. Why? Because it is the this is the difference representing the difference between xnk and znk, right? So therefore it is there in x. So we are saying y is T lambda v, which we can say is present in T lambda of x. Why? Because v was some arbitrary member of x. So therefore we have proved here that y belongs to the range of the operator T lambda. But this is a contradiction because in the very starting, the beginning of part A, we have assumed that this y is not present in the range space of the operator x, of the operator T lambda. So therefore this is a contradiction. So what was our assumption in this case? We have assumed that in this case that equation 3 does not hold. So that means we have assumed that this distance is not infinity. This is incorrect. If this is incorrect, so what is the correct thing? That this distance converges to infinity. That means the distance is never going to be a finite number. It is always going to be a infinite number. So this proves our part B. So part B is proved. Now moving on to part C, the final part here. In this case, we have to prove the main result. So that means we have to reach at certain contradiction, so which would prove our result then. So let's again have a look at our points. So in the first part, we have proved that the norm of xn minus zn is less than 2 times of delta n. In the second part, we have proved that this distance an, which is the norm of xn minus zn, converges to infinity. In the third case, we assume wn to be an inverse xn minus zn, and let's see how do we reach at the contradiction using this part C. So let's move on to part C here. So because in part B we have proved that an, which is the norm of xn minus zn, that approaches to infinity whenever n approaches to infinity. So if we set wn as some number which is 1 by an times of the sequence xn minus zn. So basically what is wn? It is the difference of the sequence xn minus zn divided by the norm of the same sequence. So if we take the norm of wn, it is going to be 1, right? So that is simple. Now because an tends to infinity and we know that T lambda of Zn is 0. Why? Because all of the Zn, they were the members of the null space of T lambda, and T lambda of Xn, that converges. This converges. We already know what was from the equation 1. your T lambda of xn, that was yn, and this yn converges to y. This we already know from equation number 1. So it follows that T lambda of wn. So what would be this thing? So if we see, this was wn. So when we apply T lambda onto this, so T lambda of wn, it would be T lambda of 1 by an times of xn minus zn, right? So it would be 1 by an, that is a number, right? A scalar. So it could be taken out T of xn minus T of zn. Now T of zn is 0, right? T lambda and T lambda. Okay, T lambda of zn is 0. This quantity is 0 because zn is present in the null space of the operator T lambda. So we are left with 1 by an T lambda of xn, right? And again this thing converges, so we are saying that it tends to 0. So this is our equation number 5. Again we can extract, because we know what is T lambda. From the definition, it is T minus lambda I. So from here we can extract this I. So when you extract this I, you have lambda inverse T minus T lambda. So what would be Wn? Wn, it was, okay, so you can write this Wn to be I times of Wn, no problem. And now we can substitute instead of I the value lambda inverse T minus T lambda, right? So it would be 1 by lambda T of Wn minus T lambda of Wn, right? So let's mark this as equation number 6. Now because T is given to be a compact operator and Wn, that is a bounded sequence. Why bounded sequence? Because this goes to infinity, right? So this is a bounded sequence. So T of Wn, this is bounded, T is compact using the compactness criteria, right? So when you apply T onto this bounded sequence, so T of Wn, this would have a convergent subsequence. Moreover, this sequence T lambda of Wn, that converges by equation number 5, right? Because that goes to 0. So this converges. So equation 6 show here that the sequence Wn, that has a convergent subsequence. Why? Because we are saying T lambda of Wn, that converges using the equation number 5, and right, and Wn is bounded. So T of Wn would have a convergent subsequence. Combining all these results, we can say that Wn would have a convergent subsequence, because we can apply the results here into this expression. The results here, right? So this Wnj converges to W. So T lambda of W is going to be 0. Just think upon this and tell me why. Okay, so here if you see T lambda of Wn, that converges by equation number 5. So let me show you what is our equation number 5. Equation number 5 is this one, T lambda of Wn, that is 1 by an times of T lambda xn, right? Now because T lambda Wn, that converges to 0, right? And equation 6 shows that the sequence Wn has a convergent subsequence, which we are calling by W. So when you apply T onto both sides, so T of Wnj, that converges to Tw, right? So from here, when you compare this equation with this equation, you can see that T lambda of Wj, that is converging to 0, and one time it is converging to T lambda of W, right? So we can say both of them, they are equal to each other. If they are equal to each other, so we can say T lambda of W is 0, and through this expression you can say that W is present in the null space of the operator T lambda, right? And moreover, Zn is also there in the null space of T lambda. So we can define another operator Un, which is some linear combination of, which is the linear combination of Zn and W, right? So because this Zn is there in null space, W is there in the null space of T lambda, so their combination Un is also there in the null space of T lambda. So if this is there in the null space of T lambda and we have defined the distance of Xn with some member Z of which was there in the null space of T lambda to be delta, which was the infimum of all those Z. So if you take some other element Un, so its distance is going to be greater than this delta n. Why? Because this was the infimum distance. So that means the distance of Xn with Un is going to be greater than equal to this delta n. So using this using all of these result here and using equation number 4 and 2, let's have a look. Equation 4 is this: Wn is equal to 1 by an xn minus zn. That means where we have defined our Wn. And what is our equation 2? Equation 2 is this one: an is less than equal to strictly less than 2 times of delta n. So using all of these result, so we can write delta n. So rewriting this equation in backward form, our delta n is less than equal to the norm of xn minus un. So now what is un? Un is zn plus anw. So we can write zn plus anw, right? So now you can write this thing to be the norm of xn minus zn minus an times w, which is this thing, right? And then what is this thing? Xn minus Zn. So if you see the definition of Wn through equation number 4, Wn Xn minus Zn is Wn into An. So using equation 4 here, we have An Wn, right? So we can take this An common. So it would be, this thing would be norm of An times the mod of An times the norm of Wn minus W, right? So from this we have this step, and because using equation 2, this An is strictly less than 2 times of delta n, so we have this expression. So overall from here we obtain delta n is strictly less than 2 times of delta n into the norm of Wn minus W. So from this expression you can write this to be 1 less than 2 times of Wn minus W, right? So from here the norm of Wn minus W is strictly less than 1 by 2. So this is a contradiction to the equation 7 by, let's have a look at equation 7. Equation 7 say W of nj converges to W, but the distance here is from here we obtain that this distance is greater than 1 by 2. So this is a contradiction because it states that this sequence Wn never converges to W. So this is a contradiction. So therefore whatever we have assumed is not true. We have assumed that, let's go back to the starting of the proof. In the very starting, we have assumed that the range space of T lambda x that is not closed is not true. So that means this has to be closed. So hence the statement of the theorem that whenever we have a compact linear operator or defined over a normed space, then for every non-zero complex number, the range T lambda that is closed in itself. So parallel to this, we have a corollary which defines this result. The corollary here, it states that under the assumptions of the theorem, that means T has to be a compact operator and lambda has to be a non-zero complex number. The range of T lambda n, where n could be 0, 1, 2. If it is 0, it is identity operator. In case of 1, this is T lambda only. In case of 2, this is T lambda square only. So the range of each of these operator is closed. This is one result. And moreover, the normed space X, that is T lambda 0 of X, that contains the ranges of T lambda X and so on. So this is the result. So I hope you understood this theorem. This is lengthy, but however the logic is quite simple. Well, that is it for this video. Thank you for watching.